Okay, so antidifferentiation is a process of finding a function y from dy dx. If you know the derivative, we can use this to find a function y. Now, I say that, we call this antidifferentiation, but I will say it's not a direct inverse because, as we'll see, there's actually going to be a number of possibilities, and we'll actually be able to get a family kind of functions that have the same derivative. Okay? For example, let's just start with a really basic one. If I told you that dy dx was 3, okay? If I tell you dy dx is 3, then think backwards. What would have a derivative of 3?
3x.
3x. Can you think of anything else that would have a derivative of 3?
3x plus 1.
Yeah. Or 3x.
Square root and then
Or 3x plus
Yes. Okay. 3x plus anything. And that's what we're going to be looking at here. There's what's called a constant. There's a constant of integration. All right. And that allows for, this is what I mean when I say we're going to have a family kind of functions that could be our function.
So kind of like when you're graphing something and you see that it can be anywhere on that line, it's like that similarity.
Well, it's basically, we know the slope is going to be 3, so it could be this one, or it could be this one, or 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 this one. All of those have a derivative equal to 3. It's just all the lines that have a slope of 3. Okay? The y-intercepts, though, might be different. Okay? Now, like I said, we're going to revisit that a little bit more as we move forward. But there's a little notation here I want you to be familiar with, and that is this capital F of x. Okay? Capital F of x is what we use to represent an antiderivative. Okay? So, if you took the derivative of capital F of x, it'll take you back to the original function f of x. If you take the integral of f of x, it gives you the antiderivative capital F of x. Okay? Does that make sense?
Wait, so. Alright, I think so.
If I just make
All right.
examples of it, that'd be better.
So,
Yeah.
well, yeah, we'll look at some examples. So here's the idea. If we take the integral of the original function, the antiderivative, don't forget the dx, the antiderivative would be capital F of x.
A word, yeah.
If I took the derivative with respect to x of capital F of x, that will take me back to the original function f of x. Okay? Now, let's think these through. All right? So, we already did one kind of like this. Let's see how well we could figure out the rest of these. If I have a cubed, if that is the derivative, what would the original function have been?
Something to the fourth power because we need to bring it down.
Okay,
over 4.
so x to the 4th power,
Yeah.
but if I took the derivative of that, it would be 4x
Yeah.
cubed.
Over 4.
So good, to get rid of that 4, I'd have to make it over 4. So 1/4 x to the 4th. Okay? So 1/4 x to the 4th would be my antiderivative. Okay? If I took the derivative of that, again, I'd have 4 times 1/4 x to the 3rd, which is x to the 3rd, which is what we were trying to have.
I think I might know the next one.
Okay? What's the next one?
Is it e to the x squared?
Not quite.
Come on,
E to
Alex.
the 2x.
You can put it over. Is it
All right, e to the 2x.
1/2 e to the
1/2
2x.
e to the 2x?
1/2 e to the 2x. Okay, let's try that. If that's our capital F of x,
Oh, cause chain.
what's capital F prime? It'd be 1/2 e to the 2x times 2, right? So that would cancel, and you'd get e to the 2x, which is what we're looking for. Okay? Now, there are going to be some rules. We're not just going to do all of these by logic. We're going to learn some rules here. But this is good to get you thinking about how the integral and the derivative work together. Okay? Let's try one more here at the end. Okay? This we could rewrite as x to the negative 1/2. That might be helpful. Alright, so what would our antiderivative be, do you
Can't
think?
just do the log of square root of x?
No.
Why not? It's 1 over, if you have like ln, then you have 1 over.
Well, if we already had the ln, then the derivative would be 1 over x. Okay? How would we take a derivative and end up with x to negative 1/2?
If you had
You
the
take
x
a
and
shut
negative
to
x.
x to the 1/2
Okay, if we had an x to the 1/2,
over 0.5. Yeah.
Times 2.
Yes, no,
okay,
maybe.
which is the same as times 2. Let's try that. If I took the derivative of our antiderivative, okay,
Come on.
we have 2 times 1/2 x to the negative 1/2. And what do you know? There we get x to the negative 1/2, which is what we were shooting for. So you see here, you can figure out a lot of these logically, knowing our derivative rules, okay? However, as we already addressed here, that's not going to be the only possibility, all right? Just using the first one here as an example, if I have 1/4 x to the 4th, okay? If I have 1/4 x to the 4th, all right, that's going to be at, oh wait, nope, it should be a lot wider. Like this. Okay?
But isn't it x
Isn't
to the
it
4th?
up and down?
It's not parabola, it won't be like.
But it has a quadruple root at 0.
Is that even possible?
Well, yeah.
Quadruple.
Multiplicity. Remember multiplicity?
How do you quadruple? Yeah, I think like how do you have 4? I'm trying to picture like what does a function look like? to have
Well,
4?
it looks just like this. Remember, if you have a double root, it kind of flattens out a little bit. If you have a quadruple root, it just flattens out even more. And if you have a sextuple root, where you have a multiplicity of 6, it just flattens out even more. Okay?
Yeah.
So, anyways, the idea is this though. This is 1/4 x to the 4th. Okay? However, we could also have
Cannot draw a curve.
this 1/4 x to the 4th plus 3.
Or negative.
Okay? Or we could have another one down here at minus 2. Okay? And that could still be a 1/4 x to the 4th, but we have a minus 2. And when I take the derivative of that, all those constants are just 0. Okay? So, we have multiple possibilities here. Okay? So, want to just practice a little bit. Trying to use some logic here. We stuck with just polynomial ones to begin with. Okay? And then I want you guys to try to develop a general rule for x to a power. Okay? So, I'm going to have you do these 7 And then from those answers, I want you to try to see a pattern and see if you can't come up with your own rule for x to a power, taking, the integral of x to the n.
Okay.
Okay?
It's a lot harder than I thought it was.
Oh, okay.
Alright, let's go through this. A lot of you guys have this. So, the antiderivative of x, if we have x, then the antiderivative,
Is 1/2 x to the second.
okay, 1/2 x squared, okay? And if we have x squared, what'd you get?
X cubed over
1/3 x cubed, good. How about for x to the 5th?
x to the 6th over 6.
1/6.
Okay. And both ways you guys said it is fine. If you want to do x to the 6th over 6, in fact, a lot of times we'll write it that way for ease anyways. Either way works. Okay, how about x to the negative 2?
Negative x 3.
The negative tooth.
The negative tooth. Negative x to the negative first power, good. Okay, which could be then written as negative 1 over x. Alright? How about x to the negative 4th power?
Negative 3 x squared.
Okay, x to the negative 3rd, and you'd be multiplying by 1 over negative 3. Okay? So negative 1/3 x to the negative 3rd, or negative 1 over 3x cubed would work. Okay? How about with our x to the 1/3 power?
3/4 times x to the 4th.
Nice, okay. So x to the 4/3 divided by 4/3 is, you flip and multiply, so it's times 3/4. Okay? And how about x to the negative 1/2? We kind of already did this one.
Yeah. 2x to x half.
2x to the 1/2, okay? So, let's think about our rule. If we have x to the n power that we're taking the derivative of, what is our derivative going to be?
You need to take the inverse of n to the in the front of x, like the
Okay,
version.
so 1 over,
N
okay,
No, 1 over n plus 1.
plus 1.
n plus 1.
Why plus 1?
Well, notice on all of these, here n was 1, we had 1 over 2.
Where?
Over here, n was the first power, so we raised it to 2,
Yeah.
and then we divided by that 2.
Okay.
Okay? Here it was 2, we raised it to 3, and then multiplied by 1 over the new exponent.
Times x to the power of n plus 1?
That's right, okay? So here's the idea, we're going to add 1 to the exponent and divide by the new exponent. Alright? So if you like seeing it this way, that works, or x to the n plus 1 over n plus 1, that'll work as well. Okay? Now, you'll notice up here though, this says that n is not allowed to equal negative 1. Why not?
Because then you get over 0.
Aha, look at that. If we have the integral of x to the negative 1 dx, and we tried to use this, we'd have 1 over negative 1 plus 1 times x to the negative 1 plus 1. It's okay to have x to the 0, but right here, you're not allowed to divide by 0. So we have a different rule for that. Okay?
Indeterminate form.
No, actually though, you guys might be able to figure this out. What function had a derivative equal to 1 over x?
LX.
Yes.
Great.
It's
so we're back to
actually-
logs. Natural
It's
logs.
watching the hope die at a big sign.
Alright,
Natural logs are like organic logs.
natural log, okay?
GMOs.
So here, look. The only difference here The only difference here is that because we're going backwards, we need to make sure x is positive. So it's actually the ln of absolute value of x. Okay? So you already learned 2 integral rules. The x to a power and also 1 over x. Okay? So, it's cool stuff. We get to do some really neat stuff here coming up.